Okay, next up in our summary of circle geometry, we have the angle subtended by an arc at the center of a circle is double the size of the angle subtended by the same arc at the circle. What that means is we have an arc, AC. And if I draw 2 radii in, there's an angle formed at the center of the circle. And if I have another angle going to that same arc, so going to the points A and B, then that angle at the circumference of the circle is twice the size of the angle of the center of the circle. And the way I write it, I say angle AOB is equal to 2 times the angle of ACB, and the correct reason is angle at the center is equal to 2 times the angle at the circumference. Now remember, it can look differently. So here I have our chord AC, and an angle is formed in the center to the points A and B, and that angle is twice the size of C. So it looks slightly different, but it has the same properties as our previous diagram. Now we're referring to the arc, the long route around. And if I form an angle at the center, that angle is twice the size of the angle formed at the circumference. Again, it looks different from our first and second diagram, but it is sharing the same properties. An angle at the center meeting the points A and B, and an angle at the circumference meeting the points A and B. So it's all the same property, but it looks slightly different. And the reason for all 3D diagrams are exactly the same. Angle at the center is equal to twice the angle at the circumference. Our sixth one is pretty simple. It says the angle subtended by the diameter at the circumference of the circle is 90 degrees. So what it's simply saying is, if I have the diameter, the angle formed from that diameter is equal to 90 degrees. And our reason is angle semicircle. But also note, it satisfies the properties of our previous example. Here we have a straight line, which is the angle at the center, which is 180 degrees. And remember, the angle at the center is twice the angle at the circumference. So you can see that 180 degrees is 2 times 90 degrees. So when we have the diameter, we use the statement angle semicircle. Next up, we have angles subtended by a chord of a circle on the same side of the chord are equal. Now let's start by the chord. If I have the chord, our chord we're referring to is AB, and it is saying that angles on the same side of the chord subtended by that chord are equal. So meaning the angles D and angle C, which are both on the circumference of the circle, are equal in size. What the word subtended means simply is that from that chord, from the point of that chord, I produce another point on the circumference of the circle. The same happens with D. So from the points A and B, we produce the angle D. So we say D is equal to C, angles in the same segment. Remember earlier we discussed what a segment is. It's the area or the space between the arc of a circle and the chord. But notice we can find 2 other angles that are also equal. We're referring to the angle DAC and angle DBC. So even though this chord is not drawn in, we still have 2 angles in the same segment. So I can put an imaginary chord in, and I can see that from D and C I produce the angle A, and from D and C I produce the angle B, and therefore these two angles are also equal, so it's the angles in the same segment, even though there was not a chord drawn in originally. Okay, now we are getting into a converse. So if a line segment joining 2 points subtends equal angles at 2 points on the same side of the line segment, then the 4 points are concyclic, meaning a cyclic quadrilateral. What that means is if I have a line, which is CD, and out of those two lines I produce two coordinates or 2 points A and B, and if those two angles which I make from CD, so remember we spoke about producing 2 points, so if those two angles are the same size, then these 4 points are concyclic, or that's a cyclic quadrilateral. And this is what it means. So I have proven our previous statement without the circle, and that is called a converse. So I've discussed the properties of this shape to form a cyclic quadrilateral, and when I discuss the properties of a shape to form or to make another conclusion, we call that a converse. And the converse which I have discussed is angles in the same segment. I was given angle A is equal to angle B, therefore ABCD is a cyclic quadrilateral. So you can say the line CD subtends equal angles, or you can say the converse of angles in the same segment. Okay, we are sticking with chords and equal angles. So now we have equal chords subtend equal angles on the circumference. What we are given is BC is equal in length to DF. And if I produce or create an angle to the circumference from both of those lines, then those two angles would be equal in size because these two chords are of the same length. But now our reason is not angles in the same segment. Our reason is equal chords, equal angles. The next one is not very often showed in class or very often practiced, but let's discuss its properties. It says that equal chords, like we had in our previous example, subtends equal angles at the center of the circle. So in our previous example, we had equal chords going to the circumference of the circle. Now we have equal chords, so AB and CD. They produce equal angles at the center of the circle. And our reason now is equal chords, equal angles, which is the same reason as our previous example. The only difference is the equal angles is now created at the center of the circle. So normally in class, we only see angles in the same segment. But from this theorem, we have discussed the converse. So if I have a line creating equal angles, then it's a cyclic quad. So converse means I've discussed these properties to create a cyclic quad. And also from this theorem, we have discussed equal chords, create equal angles, and from that same theorem, equal chords create equal angles at the center. Now lastly, we have equal chords in equal circles subtend equal angles at the circumference. Now this is our first one where we have two circles. what we are given is that these two circles, ABC and circle DEF, are exactly the same size. And we're also given that AB and DE are equal chords. Therefore, the angle C and the angle F are the same size. So we're adding on to what we had before. We say now equal circles, equal chords, equal angles. And before we just had equal chords, equal angles. Now we add equal circles, creates equal chords with equal angles.